Broadcast is now starting. All attendees are in listen-only mode.
Hi everyone. Let me first tell you how happy we are to see so many of you gathered for this webinar on the topic that we choose to present today. Note that there will be a question period of approximately 15 minutes at the end of the webinar. During the presentation, you can please write your question in advance in the question box at the right of your screen. There you go. I'm giving the floor to my colleagues who have kindly agreed to speak to you about this subject today. Polly Brown, Sales Engineer, Business Development Manager for the Southeast USA at RockTest since 2013. Specialized in hydrogeology, she has more than 20 years of experience in this field. Roberto Waldar, Sales Engineer at SMARTape in Switzerland. Since January 2000, he works in sales with a specialization in the development of markets and sales channels. Thank you for your attention and enjoy the webinar.
Hi, I'm Polly, and I am going to start out this morning's presentation on the use of distributed fiber optics for structural health monitoring. So this morning we'll cover the following topics. We'll give a brief overview of RockTest, an introduction to fiber optics sensors, detection using distributed fiber optics, and application examples. We'll go over the equipment and the technology, and then selected case studies. First, we'll talk about an overview of RockTest. RockTest is part of the Novometrics Group. It was founded in 1967 in St. Lambert, Quebec, Canada. We have manufacturing facilities in Canada and Switzerland and a presence in over 100 countries worldwide with our distributorships. With several acquisitions over time, Group RockTest is now comprised of 5 divisions, all operating under the Novometrics umbrella. In the following slides, we'll take a more in-depth look at distributed fiber optic sensing. Here's a typical monitoring scheme for structural health monitoring using traditional sensors for an earthen dam. The layout of sensors is typical of most point sensor layouts because of budget constraints. Most projects install sensors only in potential critical zones. But what happens when an event occurs outside these critical zones? As you can see clearly on this slide, problems can occur in areas away from traditional point sensors. One of the downsides to using traditional sensing is the single point nature of the sensors themselves, requiring a lot of guesswork as to what's happening between the sensor locations. In this graphic, you can see the large physical distance between monitoring locations. Another downside to this method is cost. Adequate evaluation of a large structure, such as a dam, requires an extremely large amount of sensors to be installed on the structure, making cost a primary concern for both materials and installation. In this slide, you'll see very clearly that because the distributed cable itself is the sensor, shown here as the red line, the dam can be completely covered fairly economically. Using distributed temperature and strain sensing, we can monitor for soil deformation using the strain data and for leak detection using the temperature, changes in temperature data, both with a spatial resolution of 1 meter. We can monitor the dam using distributed technology in a way that would simply be too cost prohibitive using traditional sensors. Each of those traditional sensors requires its own signal cable, and each requires its own installation effort. The distributed fiber optic cable is a continuous linear sensor. Continuous monitoring over its entire length yields the precise location of the reading within a meter, the type of data, strain or temperature, the magnitude of these data, and the precise time the events occurred. The cable has a spatial resolution of 1 meter, thereby giving the end user a data point every meter. And because the cable itself is the sensor, it provides a cost savings in both materials and installation. Also, because distributed fiber has no moving parts and is designed with a 30-year lifespan, maintenance costs are extremely low. We'll discuss some application examples now. In this graphic, you can see some of the other typical applications for distributed sensing. At the top left is an example of integrity monitoring along a bridge suspension cable. Also possible monitoring areas at this bridge are the bridge deck and the tower for deformation, and strain monitoring in the vertical cable stays. Moving clockwise is a canal or perhaps a levee being monitored for physical deformation, seepage, and overflow. And finally, at the bottom left, a tunnel being monitored for wall deformation and leak detection. In this example, we're looking at soil deformation in a slope adjacent to a rail line. The fiber would be buried in the embankment as a retrofit or new construction. In this instance, you can see the sloughing of the distributed fiber that would, on the left, that would be reflected as strain changes. Once the changes move beyond the threshold set by the client, warning messages would be immediately sent out to all key personnel, allowing for corrective measures to be taken. As you can see, the installation covers the entire slope, allowing for precise location of problem zones. Pipeline integrity is another example of long infrastructure monitoring. You can see two different uses of distributed technology here. The first is strain monitoring, as occurs with ground movements adjacent to the pipeline or in a settlement or heave scenario. The other use is temperature monitoring, when monitoring for leaks or in a situation where the pipe itself has been unearthed, exposing the pipeline to ambient air. In this instant, the temperature change is immediately reflected in the user interface and an alarm would be triggered. Now I'll hand over the controls to Roberto, who will lead you through the next session.
Okay, thank you, Polly. So I'm going to talk about the technology of the DTSS system. So this technology has been around now for more than 25, 30 years. And at the very beginning of its deployment was actually the oil and gas industry that started intensively to promote for reservoirs, wells, and downhole monitoring, and later on also for pipelines. It is now 20 years that the same technologies is used also for civil and geotechnical requirements. So a distributed monitoring system is built up on a sensing cable and the interrogator. So the interrogator is used to generate the light signal that is injected in the sensor, then to collect the backscatter light and to analyze it. After analyzing the backscatter light, the interrogator is able to show results in terms of temperature and strain, store data, and if necessary, send them anywhere using a standard TCP/IP protocol or other data transfer techniques. So backscatter light provides measurement point every 1 meter. Therefore, it can sense everywhere along the sensing cable and localize defects. The DiTeSt unit has a long measurement range up to 30 kilometers and more, and it can detect and localize change in strain and temperatures. So the advantages of the distributed technique include a large number of monitor points over a single optical fiber sensor, high resolution, and accuracy. So the scattering process is an intrinsic property of the propagation of light in the silica material from which the sensing fiber is made. So the analysis of the backscatter light consists of the combination of first the use of pulse light that enables the localization of the event along the fiber, and secondly the spectral analysis of the scatter light that provides the temperature and strain information along the fiber. So what you can see here is actually the frequency domain of a scattering process used for sensing applications. So you see the railing components, which is a pure distributed reflection with random amplitude. Then the Raman scattering magnitude is temperature dependent, and finally the Brillouin frequency shifts are temperature and strain dependent. So these are the specification of the DiTeSt interrogator for distributed strain and temperature monitoring. So the accuracy of the instrument is given by the setting of the unit, that is how the instrument is set for the measurements. The setting of the instrument is considering 4 variables, so the acquisition time, the spatial resolution, the absolute accuracy, and the measurement range. So the 4 variables are depending on each other, and the accuracy, for example, is the result of the setting of the other 3 variables. In the literature, we always mention the accuracy of 20 microstrain as a typical value, but this can actually vary according to the measurement setting. So the DiTeSt short range that you can see in this slides is the new entry-level interrogator sized to meet the increasing demand for distributed sensing. So the DiTeSt short range shows cost and performance optimized for maximum length of the sensing cable up to 5 kilometers per channel. Therefore, enable the implementation of this technology for small to medium scale monitoring projects. So this is indeed a reliable and optimized performance entry-level Brillouin interrogator for short range applications. So let's see the software. So this is the most important component of the monitoring system. So the DiView software has been developed to manage distributed data generated from the distributed sensors. So, and typically it provides system status report, informing the operator about the status of each single component as the reading unit, sensor, and the software itself. So it works continuously 24/7 without the need of an external operator. And when configured, the software can trigger alarm to a dedicated user. Warning thresholds are typically set during the system commissioning, and it provides an easy remote access to the system, offering remote troubleshooting and offline data processing. It also offers a friendly user interface with the data displayed on maps that you can see here. And the algorithm that supports the DiView software is particularly robust against false alarms caused by outlier values or noisy measurements, and it allows the whole system being sensitive to the environmental influences and unwanted variations. The DiView user interface is designed to be user-friendly, and it provides an immediate indication of the global state of the system and its components. So in order to make the selection and the visualization of each particular point, it is possible to zoom in and zoom out by simply scrolling and have information on the last measurements available, or a blinking status referring to not acknowledged warning by the operator. So let's see now the sensing cables family. So the first one is the SMARTProfile, which is a combined strain and temperature sensor. So the sensor has two fibers for strain, the blue ones, two fibers for the data communication, the green one, and two fibers for temperature sensing. So the fibers are encapsulated in a polyethylene profile, as you can see here. This sensing cable is typically used for concrete structures. So here you can see when the cable is embedded in the concrete. So first is affixed to the metal rebar, and then the concrete can be poured inside the cage. Here we see another example when the SMARTProfile is bonded on the concrete surface. So here we use a spatial glue to assure a good bonding with the hosting structure. The second sensing cable is called SMARTape, and this is a thin tape suitable for installation on a flat surface, in particular steel, metal, or on composite materials embedding. So the fibers are embedded in a composite thermoplastic tape, as you can see here, with glass fiber reinforcements, which are the small dots, while this is actually the sensing fiber that you can see here. The third cable is called Hydro&Geo, and is again a combined strain and temperature sensor. So the cable contains 4 single mode and 2 multi-mode fibers to allow the sensor to be used both with the DiTeSt unit for distributed strain and also with the DiTeSt and DTSS unit for temperature monitoring. So the sensor is particularly suitable for geotechnical applications with different methodology of installation. For example, direct burial in the underground, integration into geotextile, or surface installation in grooves. So thanks to the robust package design, the Hydro&Geo cable offers high tensile strength, crash resistance, water tightness, chemical and abrasion resistance. So here you see a few examples, the installation of the Hydro&Geo cable directly into the ground or embedded in the concrete here. So because of its robustness, the same cable is also widely used for downhole monitoring, like boreholes, piles, wells, or ground shaft monitoring. So thank you. I'm going to give again the floor to Polly, who will end up presenting a few project examples.
Thank you, Roberto. I'll discuss a number of examples now. This first project is a sinkhole detection project in Reno County, Kansas. The on-site assets are a rail line and residential subdivision located above an abandoned salt mine. Salt extraction ended in the early 20th century, but the extraction process left many large underground caverns. Some of the caverns have collapsed and sinkholes started forming above. The distributed fiber optic system was chosen to be an early warning system because it allows for simultaneous monitoring of thousands of data points using a single buried cable. This makes it possible to precisely locate and quantify the ground movement over the entire project. The detection cable was buried to a depth of approximately 4 feet in potential failure zones with an overall length of 2.5 miles. After burial, the soil was mechanically compacted to create a solid bond to the cable, allowing for efficient strain transfer. Installation of the cable was done with traditional trenching. However, due to the site's rural location, the installer discovered that the prairie dogs had chewed on and damaged several locations of the cable run. A new, more robust cable needed to be reinstalled with a more rodent-proof outer jacket. From that lesson, we developed the current Hydro&Geo cable that also has an armored version. This is a screenshot of the user interface. The limits of the monitoring zone are outlined in green. The DiView software sends alerts if the cable deformation exceeds the alarm levels set by the client. Alerts are sent by email and text message to various key personnel, including the city fire department. If there is no acknowledgement of the alert, DiView automatically sends reminders until that alert is acknowledged. In the graphic, you can see the residential subdivision to the lower left, the rail line across the top, and the salt extraction wells throughout the center. Those are the red dots. Called out at the top and bottom of the graphic is the sinkhole that was seen in the first slide and a second sinkhole found later. The Sarantino landslide in Canton Ticino, Switzerland is the next project. The landslide has a volume of approximately 65 to 80 million cubic meters. It has been intensively studied over 40 years. A possible technical solution to reduce the effects of the Sarantino landslide could be the construction of a long drainage gallery with drainage boreholes drilled from below the landslide body, as seen in the next slide. A deep borehole was at a proposed gallery alignment was drilled in order to verify the feasibility of such a mitigation scenario and to characterize the hydromechanical properties of the landslide mass, material, and displacement zones. This borehole is equipped with pore pressure and in-place inclinometer sensors, along with a fiber optic strain and temperature monitoring system. In order to reach the drilling targets, the borehole equipped with the monitoring system had to survive the local deformations for as long as possible. The fiber optic system was chosen to closely monitor the borehole for deformations during the drilling and after completion. 2 Hydro&Geo sensing cable loops were pulled down the borehole at 120 meters and 230 meters in depth, respectively. The Hydro&Geo sensing cable is able to measure strain and temperature with a spatial resolution of 1 meter all along the borehole. The robust Hydro&Geo cable is able to survive shear movements on the order of 10 to 20 centimeters. The left-hand photo shows the instrumentation being inserted with the drill rig. The photo on the right shows manual readings being taken on the site using a car battery to power the DiTeSt reading unit. The data above shows results from the short and long loops of fiber after interrogation. You can see the strain evolution of the fiber over time, where the strain increases along the horizontal axis at discrete depths. The next project is the Resolution Copper Mining Project. This is a proposed underground mine 60 miles east of Phoenix, Arizona, near the town of Superior. The project is a joint venture owned by Rio Tinto and BHP. The Resolution copper deposit ranges from 5,000 to 7,000 feet below the surface and is one of the largest undeveloped copper deposits. The ore has an average copper content of roughly 1.5%. As one of the most significant untapped copper deposits today, it is an estimated copper resource of 1.8 billion metric tons. The mine has the potential to supply nearly 25% of the U.S. copper demand. In 2008 and more recently in 2018, Resolution Copper installed distributed fiber optic cables in 2 boreholes and 1 underground drill hole to monitor ground deformation during the mining. They've recently started installing additional cables for another proposed shaft. The fiber optic cables were installed to measure strain and temperature along the length of boreholes and be read regularly after installation and during the drilling of the shaft. 2 cables are installed in a loop configuration looping up around the bottom of the borehole. They are taped to the casing as the borehole progresses to its final depth. This method allows for redundancy in the reading. The mining operator typically interrogates the fiber optic cables to collect baseline data prior to mining. This next project is Euromax. It's a new construction container terminal in the Netherlands. In the graphic, you can see the construction of a new pier section of the terminal. Of concern here is the degradation of backfill material behind the 2K walls due to the tidal effects on groundwater. 2 lines of SMARTProfile cable were embedded in the backfill material behind the K walls to detect and locate soil degradation zones over the length of the pier by detecting strain changes in the soil. SMARTProfile distributed strain sensor was directly embedded into soil during construction phases with the aim to detect backfill degradation and analyze the evolution of soil settlement. Continuous automatic monitoring with alarms was performed during both the construction phase and throughout the full normal operation. The system allowed for effective detection and location of settlement areas during the early operational phase. At the bottom right, you can see the 2 SMARTProfile fibers installed longitudinally at the normal groundwater elevation. The fibers are shown in red. The strain versus location plot in the top left shows the specific locations along the length of fiber where the strain exceedances occurred. You can see the scouring exceedance on the user interface at right and at left, circled in red, and at right, notated in red. Again, strain magnitude is reflected by color change. 2 cables were installed, 1 on either side of the pier in the backfill behind the K walls, as reflected by the 2 parallel green lines on the photo on the right. In this instance, the length of the 560 meters of cable with a spatial resolution of 1 meter yields 560 monitoring locations, many when compared to traditional instrumentation. Again, this was a fully automatic and autonomous system, sending alarm calls out when thresholds were reached. The next project is a pump storage hydroelectric facility in Switzerland. Here, a Penstock transports water from a collection reservoir down to the turbines at the power station. During a scheduled inspection, a crack was detected in a section of the underground penstock. Subsequent inspections of this penstock revealed that none of the welds were 100% free of cracks. The cracks were suspected to be due to an earth flow occurring in the adjacent soil, progressing at a geologically high speed of about 0.5 millimeter per year. Poor welding control during construction may have also contributed. 120 meters of penstock were monitored with 4 runs of DiTeSt SMARTProfile distributed sensing cable glued to the internal walls of the penstock. In terms of site coverage, SMARTProfile installation covers the entire damaged section of penstock with 4 runs of fiber, about 120 meters long. Due to the flexible nature of the cable, a looped installation method was used, visible in the top 2 photos, allowing for 4 runs of fiber in one continuous length with no splicing necessary. The concrete access tunnel to the penstock was also monitored. You can see the access tunnel in the lower 2 photos. The cable was affixed to the steel penstock with epoxy and to the concrete access tunnel with clips. You can see where the cracking occurred along the concrete access tunnel in this Brillouin frequency versus distance plot. The peaks correspond directly to the actual cracks in the concrete. Bascule Bridge in Gothenburg, Sweden is the next highlighted project. The concerns were the structure's high value, considering it is only one of 3 structures connecting the 2 sides of the river, and its age. It was built in the late 30s with low-grade imported steel from another country. During routine inspection, problem zones were discovered with cracks in the steel, and you can see that in this image over here. At the time of inspection, the bridge was planned to last another 15 years. In its current condition, the bridge was prone to failure under repeated loads and corrosion. The recommended solution was to use 5 runs of SMARTape along the entire span of the bridge, as seen in the upper photo. The support beams to which the SMARTape is affixed are shown in the bottom 2 photos, with the rightmost photo showing the tape. It's glued along the bottom edge of the steel beam. The recommended specifications from the client were very stringent. The key specifications were resolution. The strain had to be within 3 microstrain, the limit of the error within 20 microstrain, and the interrogation frequency was every 2 hours. The main peak in this plot represents the average stress over a length of 1 meter. The secondary peak represents a variation in local stress caused by a crack. The secondary peak was caused by delamination of the SMARTape coating caused by strains generated by bridge traffic at the location of a crack. Based on this technology, we can detect cracks down to 0.5 millimeter over a length of 100 millimeters. The user interface seen here reflects the strain data in all 5 runs of SMARTape. Runs B through F are instrumented support girders. Runs 1 through 5 are transition areas. In the table to the left, locations starting with N are to the north side of the bascule section, and the locations starting with S are to the south side. At the bottom of the graphic, you can see a reference drawing to scale with the data above it. This next project is an automobile tunnel in Switzerland. The A2 motorway, also called the Gotthard route, is one of the most important north-south transport arteries in Europe and one of Switzerland's busiest motorways. Water accumulated behind the concrete lining, causing a portion of the lining to collapse in June of 2017 due to the hydrostatic pressure buildup behind it. Further investigation showed that the cause of the issue was meltwater percolating through the rock mass and collecting behind the tunnel lining. The decision was made to monitor both walls of the tunnel with SMARTProfile for tunnel wall deformation to predict potential failure zones. Further remediation was performed at the failure zones, installing drains. In this photo, one line of SMARTProfile fiber optic cable is now tightly affixed onto each tunnel wall using clips and allowing for strain detection and location every meter of concrete lining. Any deformation or crack formation due to hydrostatic pressure behind the lining will be easily identified, allowing for mitigation efforts. It's also worth noting that because distributed fiber optic cables are very flexible, with a small bending radius, they can follow problem zones easily. No need to install them in straight lines, making effective coverage very easy. The cracks in the photo are highlighted by the red arrows, and you can see that the fiber optic cable goes across the cracks perpendicularly. Strain variations in a localized section of the tunnel can be seen here in this microstrain versus location plot. Strain peaks are directly correlated to small individual cracks in the tunnel lining, as called out by the red arrows. This screenshot of the user interface shows a plan view example of strain data. The color scale at the right indicates the magnitude of the strain. Two different sections of the tunnel are instrumented in this case, one on the right side of the drawing and one on the left. Both tunnel walls are instrumented, as seen in the section to the right, signified by the two green parallel lines. The left side of the tunnel is where the bulk of the exceedances occurred, and you can see that those in red. The next project is a gold mine in Australia where deformation and settlement monitoring of the operating tunnels and laterals was discovered. Distributed sensing was used to detect and evaluate mass rock behavior throughout the tunnel matrix during construction and operation. The end goal was to increase the safety factor and increase production efficiency. 3 main operation tunnels were instrumented with a total of 7,000 meters of Hydro&Geo strain and temperature sensing cable. The Hydro&Geo sensing cable was installed with the goal of providing a good bond between the cable itself and the tunnel structure, thereby ensuring good strain transfer and high sensitivity from the tunnel surface to the sensor. The cable was affixed to the walls with plastic and metallic clips and onto the mesh behind the tunnel lining using cable ties to facilitate proper orientation behind the lining. The layout of the fiber can be seen as the white lines on the 3D blue rendering, tunnel rendering on the right. After installation, the cable was covered by a shotcrete liner. The next project is a platinum mine in South Africa. The Mototolo tailings dam is part of the Der Brochen platinum mine located in South Africa in the Limpopo province. The immediate area around Mototolo is rapidly developing into a major mining district with many new platinum and chrome mines. The Mototolo tailings storage facility is an expansion to the current mine infrastructure to accommodate the storage of future tailings. Mototolo is a hillside tailings impoundment of 115 meters in height with a maximum footprint area of 1.4 square kilometers and is capable of storing 65 million cubic meters of tailings material. This graphic shows a plan view with elevation contours. The Hydro&Geo cable installation is depicted in red near the bottom of the drawing. Approximately 8 kilometers of Hydro&Geo sensing cable for strain and temperature monitoring were installed during dam construction. The cable was installed at the liner soil subgrade interface for strain monitoring in the liner and seepage detection due to liner defects. Monitoring was performed during the construction phase for quality assurance and later for structural integrity and leak detection during normal operations. Measurements are carried out automatically and fed into the data acquisition software. The software DiView is able to show the results remotely and also trigger alerts via the SCADA system, SMS, email, or phone in case of critical events. Again, you can see the Hydro&Geo cable depicted in green at the bottom of the user interface and the strain magnitude scale on the right. At the far left, you can see a photo of the instrument cabinet containing the fiber optic interrogators, the server, the battery backup, and the communications equipment. Most cabinets are climate controlled. The final project is one of our more recent ones, the Canarsie Tunnel, a twin-tube tunnel running on the L line of the New York City MTA subway network, links Manhattan with Brooklyn under the East River. The tunnel was flooded with salt water in 2012 during Hurricane Sandy, resulting in damage to utilities and the concrete duct banks running the length of the tunnel. The initial plan was to rehab the tunnel involved closing the tunnel for 18 to 24 months, but because of public uproar, the governor commissioned a committee to develop a new plan. This second plan involved relocating the utilities higher on the tunnel walls and encasing the dilapidated duct banks behind reinforced fiberglass panels, RFPs. A system of Hydro&Geo sensing cable with a total length of more than 4,000 meters was affixed onto the encased duct banks, the RFPs, monitoring for the deformation. The photo on the left shows the condition of the tunnel before repairs. The photo on the right shows the application of epoxy to affix the Hydro&Geo cable on the tunnel walls and RFPs. In a typical installation, the epoxy is more than sufficient to permanently affix the cable to the structure. But in this application, we were told by the MTA personnel that we would have to protect the cables from rats who apparently like to chew through cables similarly to prairie dogs. Consequently, a second layer of an impervious epoxy resin was applied to protect the cables from rodent damage. During the design phase, RockTest engineers installed a demo proof of concept installation mock-up in the tunnel to try out several epoxies and epoxy resins. The installation of Hydro&Geo cable from a work train is on the left. On the right is a detail of the Hydro&Geo cable with the protective resin over the top. The overall installation took place during select overnight weekdays and weekend tunnel closures. From start to finish, the entire project was done in a little under 12 months, with train traffic continuing during every workday. The initial estimate for the mediation was 18 to 24 months with complete closure of the tunnel. Thank you. Thanks for your attention.
Excellent, Polly and Roberto. Thank you for the presentation. We will now move on to some questions that some participants have asked. Let's start now by giving the floor to our colleague, René Deblois, Sales Director at RockTest in Montreal.
Thank you, Jennifer. We do have several questions. The first one would be, what would be the cost for a typical project with fiber optic?
Yes, I can I can reply. Well, for small, medium-range projects like, for example, the Penstock tunnel or the highway tunnel in Switzerland. So for a permanent and automatic installation, we are around 100,000 USD. Then for the mining extraction tunnel in Australia, we are around 150,000 USD. And finally, for the tailings dam in South Africa, we are about 300,000 USD. So these are the range, yes, of prices.
Thanks, Roberto. Another one more specific to a project. How long did it take to install the cable on Canarsie Tunnel project?
I can answer that, Renee. Installation of the cable took about 80 to 100 hours. And the whole project, as I said before, was about 12 months, and that included train traffic still running during the days, so that the cable was installed working overnights and on the weekends. And it was certainly a lot shorter than the 18 to 24 months that were predicted with the full tunnel closure originally.
All right. Another one's more general. Why someone would choose SMARTape over the SMARTProfile? I
can answer that one too. The SMARTape is more suitable for the steel. It's thin and not as pliable as the SMARTProfile, so it can be actually more easily glued onto steel or metal. It also is used when there is a higher accuracy that needs to be received. And the SMARTProfile is more pliable, and it's better for mounting in concrete or embedding in concrete. And it has a plastic bonded material to encase the fibers, and it also contains 2 communication fibers that can be used.
All right. More technical one, more specific one. What happened if we break an FO cable, fiber optic cable?
Yes, I can answer this one. Yes, well, the cable can be easily repaired on site using, for example, a portable splice machine. In case we have no access to the cable for repair, well, for example, when it's buried in the soil, deep in the soil, it is still possible to resume the functionality of the cable by switching to BOTDR mode and read the cable with one channel until the cable breakage, and with the second channel on the opposite direction of the cable loop.
Okay, maybe one last one. Is it possible to get movements in millimeter or inches from strain measurement?
Yes. When the sensing cable is buried, we typically have quantitative information on the soil movement, like the location along the cable of the event, the location of the event, and the evolution of the deformation as a function of the time and space. To quantify the movements, for example, in millimeter, we need to combine the distributed sensing with, for example, an extensometer or a settlement soil gauge. So we need to combine 2 different systems together.
Okay, well, thank you very much, Roberto and Polly.
Yes, thank you once again, Polly and Roberto, for your answers. Unfortunately, time goes by, and we appreciate all the questions you sent us. We'll answer your questions directly to each one of you by email in the outcoming days. Thank you very much, everyone, for taking time today and showing interest in our webinar. Hoping we can collaborate in future projects together. So if you have any question or for more information, feel free to contact us. Again, thank you. It was a pleasure for us.